So we went over deforming the surface by trying to sort of like refine the surface to make a better estimate of where the gray-white matter was, and also the peel surface. And I'll just go back and just say one thing about that. So way back in the day when we first tried to reconstruct the cortical surface, we said, why don't we just shrink something, a known surface, onto the cortex? And then we were hoping that we would be able to get that surface, here's that surface, to sort of go down into the sulci. But the problem with that approach is that these surfaces approach each other too closely, especially in the younger person. There's almost no space at all between one bank of the sulcus and the other bank of the sulcus. And so because of that, it's really hard to sort of stuff this surface down in there. So we just use that for getting rid of the skull, but not actually reconstructing the surface. And so instead, what we did is we aimed for this surface right here, which doesn't approach itself as closely. But we still need to try to estimate this peel surface. So this one is the peel, and this one is the gray matter, white matter over here. So we still need to estimate the peel surface. And the way you do that is you turn the image data down to dark so that the surface will float up until it sort of hits the dark. And then when it hits the dark, then it will stop. But there's still a problem with a situation like this in a very young person. A young person looks like that. There's no space at all. And so what you do in order to estimate the peel surface is you stop the surface from intersecting itself. So basically, the surface sort of floats upward. And why does it float upward? Well, it turns out the cortex is less myelinated up here than it is down here, so it's actually a little darker as you go up, and so there will be a little bit of a force to move that gray-white matter surface up. And then basically, if it runs into the other surface, it stops. So that's essentially how the peel surface is estimated in the sulci. The peel surface, no problem estimating the peel surface on the gyri out here because it's dark outside there, but it's more of a problem in the sulci. So it's a little bit of a hack, but works pretty well. And so that was just sort of following up on the last of the previous lecture about refining the surface or inflating the surface. So what we're going to talk about today is aligning surfaces. And so one of the big things that people do when they scan people is they want to sort of find the same place in multiple people. So I want to find, say, area MT. It's an area that's involved in motion and motion processing. It can see very low contrast. If I'm going to record from one person's brain, record from another person's brain, and compare the data, or average the data, or do statistics on the data, I need to somehow find the same place in different brains. And the standard way of doing this that I mentioned was to take a brain in 3D and sort of make it look like another brain in 3D. But the problem with that is that, as you mentioned, is that sometimes, somebody has a superior temporal sulcus that looks like that. Sometimes somebody has one that looks like that. Sometimes somebody has one that looks like that. And so in this region right here, there's going to be a lot of variation in the 3D location of the cortex. And because of that, the 3D methods have a lot of blurring associated with them. And so the idea is if we could somehow align brains using the surface instead of 3 dimensions, we would do a better job. And so we got the idea of how to do this years ago, like 25 years ago. It was, I always like to say, it was Anders Dale, who was my student at the time, who wrote most of the software, and basically added one line of code to do this. And what that one line of code was to essentially try to determine where the sulci were on the surface. Now, that sort of seems like a reasonably straightforward thing to do, but it turns out it's not completely straightforward. And so the idea was if we could find where the sulci were, then we could use that measure of how much like a sulcus you were to drive the alignment between branes, and that would help with dealing with these problems where one was a sulcus and one was a gyrus. It wouldn't like that, but all the sulci and gyri around it would kind of like jockey everything into position, and then the constraints on keeping the surface from getting squished would also keep the surface relatively stiff, and then you'd end up with a mapping between two branes. And so the way this works is we start off with subject 1. So here's subject 1, and reconstruct their brain. And so here's their brain, and they've got little folded sulci of various kinds. And then here's subject 2. So reconstruct their brain. And they're different. Say this one had that kind of STS, and say this guy had this kind of STS. And say this one had a post-central sulcus and a separate sulcus, and this one just had an interparietal sulcus. So they're all different sizes, and et cetera. You do a couple of those. So then what we do is inflate the brain. And so if you're using FreeSurfer, this surface is called smooth white matter. And smooth white matter. And then we inflate it. Now, inflating it is not really quite the right word. So what we want to do is inflate without stretching. So if you take a balloon that's deflated and you blow on it, what will happen is it will first sort of just expand out to balloon shape. But if you don't blow real hard, what will happen is it won't get any bigger. And then if you blow really hard, suddenly the balloon rubber will kind of like relax and the balloon will blow up. The process that we use for inflation is similar to that first part without stretching. So it's basically just blowing up the cortex surface, but not stretching it at all. So you want to preserve the area of the cortical surface. And so when you do that, you get a bigger brain. And this is where, like, here's the central sulcus, and now the central sulcus will be opened up. And here's the superior temporal sulcus, and here's another little sulcus slit. And so the superior temporal sulcus will be opened up like that. And then the lateral sulcus, where the insula is, will be opened up like that. And so you'll have a smooth surface that has all the sulci opened up on it. And so subject 1, so that's the generation of what in FreeSurfer is called inflated. But like I said, it should be more like unfolded is more correct, because you're not stretching it. So that's inflated, and so we can inflate another person down here. Maybe this guy was a little bigger. So here's this person just has a regular post-central sulcus and a little interparietal sulcus slit, and maybe this one had an STS that sort of comes to the surface and then a little bend in it, something like that. So in order to align things on the basis of sulci, the problem is you need some record of where the sulcus is. And it turns out that's just a little non-trivial. So let's look at, a sulcus here. So here's a sulcus, like that. There's the gray matter. Now, so where is the sulcus? So that's a good question. Is it right where it turns in, or is it sort of like down here, Or is it like until you get over here? It's not totally straightforward to define it. So one thing you could do is you could shrink a surface onto it that was very stiff, and then just try to measure the depth, like measure the depth until you run into the cortex. That might be sort of a complicated way of doing it. Or you could do one line of code, and what that one line of code is just measure how far the surface moves when you inflate it. So if we've got if we have our surface here, say, put a surface in the middle, say in the gray matter. Okay, so here's our surface, and we just inflate that, meaning expand it without stretching it, and then just measure how far each vertex moved. What do you get? Well, you'll get something, this is about the right scale of what the brain looks like when you inflate it without stretching. It sort of looks like it's got about twice as big, something like that. About maybe 70% of the cortex is down in the folds. So you inflate it, you get a surface like this, nice smooth surface. So this guy is, there's another surface called gray mid, which is like halfway in between the peel surface and this is the pia. It's called the pia, and this guy is inflated. So what will happen when you actually look at individual vertices? Well, this guy down here is going to come up to here, and then this one is going to go out to here, and this one is going to go over to here, and so on, something like that, and this one's going to go over there. So all you have to do, the one line of code is just measure how much you moved. So each vertex moved. So if this vertex down here is going to move a longer distance than a vertex that's on a gyrus, and that's a kind of a nice measure because it's a nice sort of floating point measure. So it's a nice smooth measure. So the deeper you get into the sulcus, the deeper, the larger this number is going to be. And so if you look in FreeSurfer, so basically it's the distance each vertex moves during inflation. And so if you just measure that, then that's a good measure of, so we can call that sulcusness. It's like how much like the more you move, the more like a sulcus you are. But it's a nice sort of smooth number. And if you look in FreeSurfer, there's two different sort of measures of the curvature of the cortex. One is the actual curvature, which you talked about last time, and what was the curvature? That was look at one vertex here and compare it to its neighbors. And so if we do that, we can see that this central vertex is slightly out. So it's slightly convex relative to its neighbors. So that measure is called, in FreeSurfer, is called curve. So this one, this one is, sulc. And that's this distance. But you can also look at curve, and curve is very local. So curve is just local, and this one is a some movement. And so you could try to use curve to align brains, but that's a very wiggly little thing. There's all these crinkles in the cortex as it folds, and those crinkles aren't particularly diagnostic of anything. They're sort of idiosyncratic, different between different people, just how after a sulcus forms, it then crinkles up. And so the curvature will show you all those little crinkles, but who cares about them in a way? And so if you just look at this total amount that each vertex moved, it gives you more or less, something that tells you how much like a sulcus something is. So, but it's, it's got the advantage if it's not a very deep sulcus, then it's not as strong of a number. And so the idea was, let's use that to line up brains. And so when I first did this, I said, well, what does the brain look like after it's been inflated? It sort of looks more or less like an ellipsoid. If you look at an inflated brain, it's not quite, but it's kind of really elongated that way, and then it's pretty elongated that way, and it's not very elongated left to right. So I first started forcing the brains to be an ellipsoid, and then try to align the ellipsoids. But that's kind of nasty dealing with ellipsoids, the way that the surface moves on ellipsoids. And so Bruce Fischl rewrote this in the distributed FreeSurfer to do it on a sphere. And so the idea is, what you would do is you would first now force everybody into a standard sphere. And our standard sphere is like a 10 centimeter diameter sphere. So so blow everybody up into a sphere. And you'd still have all the sulci on there. So if you look at these spheres, after a while you can see, oh yeah, I can see it just looks like a lateral view of the brain. Here's the STS. Here's the lateral sulcus here. There's one of the frontal sulci. So basically, blow everybody up to a sphere. Now, each sphere is going to have a different number of vertices. So they're all going to be, slightly different from each other. So you have to deal with that somehow. So that's sphere. So let's just draw the situation that we're dealing with. So the goal is we want to sort of align everybody with an average brain. And so how would you do this? You might sort of bootstrap by first aligning everybody to one brain, and then make an average brain out of that, and then align like an average sulcus pattern out of that. And then you could start again and align everybody to the average. You could sort of bootstrap it, the same way you would do with a 3D data set. You'd have to, in order to generate an average, you initially have to just pick one target and align everybody to that, and then eventually, align everybody to the average. So let's assume that we got an average sphere that had the average amount of sulcusness at each point on the sphere, and then we could align everybody's individual sphere to that average sphere. So there's two things here. So first of all, what does the average sphere look like, and how does the alignment process work? So we'll start with, what the average, what the one true sphere looks like. So here's the one true sphere. So the problem is, if you think about these brains, each one has a different number of vertices, because the number of vertices just comes from however many voxels there were in the white matter. And some people's brains are bigger, some are smaller, some are more folded than each other. So they've all got completely different numbers of vertices. And so if we want one true sphere, we need some kind of sphere that has like a fixed set of vertices that we can align everybody to. And the way that you do this is to subdivide a sphere into a bunch of triangles and a bunch of uniform triangles. And One way of doing it is using something called, a subtessellated icosahedron. And if you look, this is basically a geodesic dome. And so what is a geodesic dome? Well, there's a number of different surfaces that can fit inside a sphere and have the corners of that surface touch the sphere. So a cube is an example. So you can put a cube inside of a sphere, and the 8 corners of the cube will touch the sphere. Or you can put a tetrahedron in a sphere. So what's the shape with the most faces that you can fit into a sphere? It's an icosahedron. And so what does an icosahedron look like? It looks like, if you look at it from the top, it's got 5-fold symmetry like this. So there's 5 triangles from the top, and then you can see the faces sticking out below, a little bit below like that. So it's basically got 20 faces. So it has 12 vertices and 20 faces. That's the icosa part. And if you look at it from the side, you can see you'll see, like, here's some of the triangular faces from the side. And here's you can see the faces sticking out the top. So that's a nice regular surface. Each one of those 12 vertices hits the edge of a sphere. And so then what you do, but that's not a very good estimate of a sphere. So what you do is, let's just take one of those, just blow up one of those 5-fold symmetry parts. So what you can do is you can take each triangular face, and so here's the vertices that actually touch the sphere. So you take a triangular face like that, and then that gives you 3 more vertices, 4 faces, 3 more vertices, and then you can promote those vertices to touch the sphere. And then you can do that again, like that. And then you can do that again, like that, and do that again. So do that 7 times, and you'll get 160, roughly 160,000 vertices. And so each time you promote everybody out to a sphere, so you end up with an estimate of a sphere. It's a slightly weird kind of thing, because you notice that there's 12 vertices that have only 5 faces around them, but then every other vertex has 6 faces around them. So it's slightly asymmetrical. There's a couple special vertices, and if you go to one of those space theaters, Omnimax theaters, this is what the screen looks like. So if you just look out at the screen before they start the movie and try to spot the 5-fold, there's just a couple vertices in that screen that have only 5 triangles coming out of them. Everyone else has 6. So basically, that's what the one true sphere looks like. It's got like 160,000 vertices, 10 centimeters in diameter, evenly spaced. The vertices are all evenly spaced. So now the problem is we need to align these guys to that sphere. And so what's going on there? Well, so we've got, that's a little bit of a hairy problem. So we've got one mesh. So here's, one mesh, bunch of triangles. And say this guy, this green mesh is the one true sphere. And then we have somebody else's mesh. So here's another mesh. So say this one is one of those individual surface meshes from one of the subjects. It's, whatever, it's a complicated mess. Okay, so we got that mesh. And so basically what we want to do is, so this guy, say, one true sphere, and this guy is subject N. That's still a sphere, so we turned subject N into a sphere, but now we're trying to sort of align two spheres to each other, and using this measure. And even though it's only one line of code, it gets you about like 90% of the way there. There's all different kinds of little additional tricky things you can do, but this kind of like does most of the work, sort of gets most of the sulci lined up, and it does a much better job than trying to do it in 3D. So basically all you do is, so in words, what are you doing? You're just trying to, so this guy, subject N, is movable. And the one true sphere is fixed. So basically what you want to do is somehow get the, go in whatever direction you need to make this vertex have its sulcus measure be more similar to the target. So this guy is, this guy is the target. And, this guy is, what do they call it, subject, this is one subject. So basically we want to, distort the subject into the target. And so what we want to do is like, which way do I need to go to get my sulcusness to look more like whatever the sulcusness of the target, the average sulcal pattern is. And so I'll write down here, how we can do that. But the bottom line is that we would then still have a sphere, so it wouldn't change the shape of it, it would just move stuff around. So now remember, this would still have different number of vertices. So now we've slightly moved things around a little bit so that everybody's all lined up with each other. But we still have different number of vertices in here. So if you look in FreeSurfer, this one is called SphereReg. So that one is, it's still a unique number of vertices for each subject, but it's, but now it's registered into alignment with the average sulcus pattern. And so once we've done that, then we can finally map everybody onto the one true sphere. So here's the one true sphere. One of the, I'm just sort of joking about one true sphere. There's like multiple spheres, but one of the surfaces is called, FS average. So FreeSurfer average sphere. So to get to that, however, you notice there's a problem. How do we get to that? There's a different number of vertices. And so in order to align everybody with, the one true sphere, we have to do some kind of sampling. So after we've done the alignment, we then, the vertices are not going to be on top of each other because there's different numbers of them in different branes. And so what we need to do is we need to take, so say you did some fMRI data and there's a statistic associated with this, with say this, so say we've got some, stat associated with that individual subject stat. So individual subject stat. So what we can do then is we have to sample it back to the one true sphere. And so it's closest to this guy, so we could either sort of send a little bit of it to these other faces, or just send it to the closest, to the nearest neighbor. And so basically you would sample that statistic from here, onto the one true sphere. And then once you have it on the one true sphere, then you can do statistics like you would do in 3D if you had aligned branes. Then you just have a 3D location, and you could look at those statistics across subjects, because now it's one true sphere, and so now you're hopefully got everything lined up so that you can go. So each vertex will be the same across all the different subjects. So how do you do this? It's not very hard. It's very similar to what we were talking about before, and so we have to define an error, like an error function. So here's another error function. We'll call this one sulc, sort of the sulc error. And so what is our definition of that? It's going to be, something across all the vertices. So it's a sum across all the vertices of all the centers. This is 2D centers now, so it's not 3D, 2D. So we sum across all the vertices, and so what are we summing? Our error is just defined as the difference in sulcousness, because our average sphere is going to have a set of sulcousness measures at each vertex that will tell it like how much like a sulcus, each vertex, 160,000 vertices in the sphere have. And then we'll have a given surface sulcousness, and it will have, our alignment will have tried to have gotten it lined up, but it won't be exact. And so we have two different sulcousness. So here's the sulcousness, of a subject. So that's the sulcousness of a subject, at a particular center vertex, minus the sulcousness of the target. And this one, for the purposes of the derivative, is going to be our variable. So this one is because we need to go in whatever direction will make our sulcousness more similar to the target. And so that means we've got to sort of go out in space a little bit, take a derivative and go out in space a little bit to figure out which way to go. And so that one's the variable for when we take the derivative, and then squared. So now that's just one term. So we're going to also keep those other terms that we had last time. So like try not to allow the surface to get squished up. So this individual surface. So when we're doing this process of, aligning to this target sphere, we don't want the surface to get all bundled up where the vertices are all crammed together. There's going to have to be, whenever anybody looks at these surfaces, they say, well, it looks kind of squished. And sorry, that's just part of the job. There's got to be some squishing. You cannot avoid any squishing because people's brains are different. Some parts are a little bigger, some parts are a little smaller. So if you have a little bigger part, obviously it's going to get squished when you head to the average if it's smaller on average. So there's always going to be some squishing, but we will adjust the weight. And there's a little bit of a play there, because you can decide how much should I try to preserve the original, how much should I sort of stop it from squishing, and how much should I line it up in sulcousness. Those are, up for discussion, like what's the best, possible combination of making it line up with the average brane but not squishing it too much. So this is just one member of the, so remember we had, the total J, was J equals, J. There was a normal one plus J, there was a tangential one. That was the squishing one, plus maybe, plus a bunch of other ones. So this is just another one that we're adding in there. We don't have to worry about the normal one because we'll force it to be a sphere. It can't be anything but a sphere, so you don't have to worry about its curvature changing. But the tangential one is important because that one will determine, you know, how good do you align to the target, but also how squished were you? And those are sort of negotiable. You can decide for taste. Do you want to really get good alignment, or do you want to just get pretty good alignment but not distort the individual surfaces too much? Okay, so that's our error, and then we take the derivative of that, which tells us which way to go, and we take the negative of the directional derivative of that guy, and with respect to these center positions, these are 2D. So rather than 3, there was 3D last time when we were doing the deformation, and so that's going to equal, you know, some parameter, which is, you know, how much should we value the reduction in error of sulcusness, and then times the derivative of that thing, which is going to look like the image, very much similar to the image guy. So there's going to be this individual subject sulcusness at a vertex. You know, so when you take the derivative of this thing, it'll be, you know, this. You'll take this, stick it out in front, the 2, reduce the power 1, and then take the derivative of this, multiplied by the derivative of this. And so, so here's that coefficient basically, which is unchanged. And then it will be multiplied by the derivative of this. And since this thing is constant, this is the sulcusness of the individual subject vertex. But this thing is effectively the variable, and so that's the one that we'll have to take, you know, use the chain rule to take a derivative of. And so we'll get the same thing we got last time, which was the gradient. So the gradient just means the fastest changing direction in sulcusness. So it's and the negative is in there because we subtracted it. It just depends on, you know, you wouldn't have a negative if you flip the subtraction. You can write it out different ways. Okay, so what is the gradient? What does that mean? What's the gradient of the sulcusness? So that just means what is the direction that the sulcusness changes the most rapidly in? So what would that be over here? So that would, you would just, and on the target, so on the fixed target. So it would be, you know, go to this vertex, and then look around that vertex, and figure out which way the sulcus measure changes the most rapidly. That's what the meaning of the gradient is. It's a 2D, this is a 2D gradient. And so say, you know, it changed very rapidly in this direction, less, you know, in these other ones as we go to these other vertices. So, you know, maybe something like this. So that this will be the, you know, the gradient in sulcusness of the target. And so that's a vector. So you start off with, and I'll talk on the Friday 8 a.m., I'll talk about, you know, what is completely write out a gradient so you can see what it is. So what a gradient does, what this gradient operator does, is it turns sulcus, which is just a number, into a vector. So this guy, you know, is a gradient vector. And we calculate it by figuring out what direction does the S, sulcusness, change most rapidly. And then how rapidly is that most rapidly? Because it could just be a shallow change or a big change. And so the length of the gradient vector is how rapidly it changed. The direction of it is basically what is the direction that it changes the fastest upward. So so basically what that will tell us, so if we look at this here, this thing is a scalar. This basically just says, you know, how much should we move? Like, were we really off? You know, were we really off here? Like, was the difference between the target and our current vertex, you know, really off? Or was it just a little bit off? So that's a scalar. And then this thing gives the direction. So this guy's a vector. This is, you know, which way to go. It's also got an amplitude in it. So, you know, it could be that because it depends, this whole amount that you have to move, the vertex depends on, first of all, how far off were you? That's one thing it depends on. But the second thing it depends on is what is the steepness of the actual change in the target. Because if the target is changing very rapidly, you won't have to go very far in order to essentially get to a higher sulcusness. Say we're looking for a higher sulcusness, and the gradient in the target is very big. That means that a small movement will cause a large change in sulcusness, so you don't have to move as far. So both of these things, you know, factor into it. But then, you know, if you do that, you basically just run this, then you can essentially get this surface, this red one, as aligned as possible to the one true surface. And then after you've done that, then you can start sampling data onto this surface. And what will you know, end up with? You'll end up with, you know, here's icosahedral, you know, vertex, you know, number 1. And what is that going to have? It'll have data from each subject. So here's subject 1. And there's going to be a whole bunch of data from subject 1. So there'll be, you know, whatever the sulcus measure was, because that won't necessarily be the same as the target. And, you know, what the curvature was, what the 3D coordinates of the vertex, you know, 3D original coordinates. This will be useful too. There'll be some stats. You could have a whole time series if you wanted to. You know, before you calculate the stats, maybe we want to do something across subjects with the bare time. You know, and so on. There'll be a whole bunch of different things from that subject. And then here's, you know, subject 2, and that will, you know, have, you know, everything, same on that, etc. And then we'll have, you know, ico, vertex. So it's all in this somewhat strange list structure. And so you'll have, you know, subject 1, subject 2, you know, all across those 160,000 vertices. So basically that will allow you then to do, you know, stats, just regular kind of stats you would do across subjects once you've got everything sort of lined up into this system. So. Okay, so any questions about sort of how that works? We'll talk a little bit about sort of displaying the data and various problems that you get with displaying the data, but are people reasonably clear on this? So you don't have to worry about the equation so much. I mean, it's just basically how does it work? It's very intuitive. You know, you've got a vertex here. It's got a certain sulcus measure. What direction do we need to go in order to make it more similar in its sulcus measure to the target? How do we figure that out? We've got to take a gradient of the target in order to figure out, you know, which direction should we go. So if we wanted to go to a higher, a higher amount of sulcusness, well, we just need to know what direction is the higher amount of sulcusness, and that's what the gradient measures. And then all at the same time, trying not to distort the surface too much. So, you know, there's going to be a little resistance to moving in that direction because this triangle is already kind of big, whereas these guys are a little smaller. And so, so there's, if you move in that direction, it's going to make the surface a little bit more distorted. And so those things will sort of play off. Now, again, it's a very brain dead method. It's just completely local. So every vertex for themselves. Everybody's just trying to reduce their sulcusness error, and also at the same time reduce their squishing error. Okay. So once you've got it onto this, notice that once you've got it onto the sphere, all the data onto the sphere, we could paste the data back onto any individual brain we wanted to. Because all we'd have to do is just do the reverse sampling, like sample back onto the individual subject's sphere. And then once we're on the individual subject's sphere, then we could just go back to what, vertex 439, which will be the same. And so we could display the average data back on an individual subject, or we could display the average data on any inflated subject. Okay, so any questions about that? So, and you only have to do this, if you get a subject, reconstruct them, inflate them, sphere them, register their sphere, and then put the data, onto the one true sphere, you could, collect multiple scans on a person, and you only have to do that process once of, aligning the brains. Now the problem is, how should we look at this? And it turns out there are several different ways of sort of looking at the data. And for whatever reason, people just don't like to look at the one true sphere because it doesn't look like a brain. It looks like a sphere, and so it's kind of hard to tell. You look at that and you say, well, it doesn't really look much like a brain. And so what can you do? So one thing you can do is you can take these original 3D coordinates, because you've got those, and now they're in the one true sphere format. And so you can average the original 3D coordinates and get an average brain. And so if you do that, so basically, how does that work? So you go from, folded individual brain to inflated, and then so we go. So we take the folded 3D coordinates. So average. So if we take, what are we averaging? We're averaging, average 3D, original 3D coordinates using one true sphere. So we got 20 people. We aligned them, turned them into a sphere, aligned them to the average sphere, sampled their 3D coordinates onto the one true sphere so we could average them, and then average them vertex by vertex, and then draw a surface of those average 3D coordinates. And so basically we can, after we've averaged those 3D coordinates of smooth white matter. So average the 3D coordinates of smooth white matter, and then we'll get we'll basically, get an average smooth white matter. Now, what's the problem with that? Well, there is a problem with that, and then we could, after we've done that, then we could inflate this guy. And if you look in FreeSurfer, there is a surface for this FS average sphere. And what is that surface? Well, it's a surface made by taking a bunch of subjects, registering them to the sphere using sulcus, and then sampling the 3D coordinates onto the sphere, averaging the 3D coordinates, and then drawing a surface. So what will happen if you do that is that, remember, the sulci are all sort of crinkled up like that, like the STS. And here's another subject, another subject looks, different, sort of randomly different, and here's another subject. And so when you average all those crinkles in the sulci, what do you get? You just get a straight STS. Like the STS, if you look at the STS in this average smooth white matter, it's completely straight. That's going to unfortunately lose some surface area. It loses about a third of the surface area. And so, so what's the problem? This is a shrunken brain. Shrunken brain, because that. So when you average all those, when you average out all the little sulcal crinkles, you lose surface area in the sulci, and it's also not good because you're losing surface area selectively in the sulci, not in the gyri, because the gyri aren't as crinkled. So shrunken brain, with selective loss of surface area in the average surface in the sulci. So if you're trying to display data, that's not good, because then what's going to happen is it will slightly sort of squish the activations in sulci. And so what's the right way to do it? Well, it was sitting there for years. Nobody really used it. Now you might wonder, why would anybody use the shrunken brain? Well, one of the reasons people use the shrunken brain is because sometimes people don't want to mess with the whole doing statistics, on the sphere business in this list of vertices on the sphere. And what they want to do is just use their regular 3D statistics packages, and then after they're done doing everything in 3D, sample it onto a surface for display. And that way you can sort of make a nice, picture of the sphere without going through the pain of dealing with these lists of vertices. But that's kind of sort of not as morally upstanding as sort of doing the right thing and actually sort of sampling things to the surface. But in that case, you have to use this average smooth white matter because you've averaged the data in 3D, and if you want to sample it onto a surface, you need an average surface to sample it onto. But a different way of doing this is you've got the folded brain, and then inflate each brain. So this is, folded N brain. So, you basically average the coordinates, so here's folded 1 and folded 2, etc. So you average the coordinates, the 3D coordinates. But what you could do instead is you could take folded 1 and inflate it, and folded 2 and inflate it, and then average the coordinates of the inflated. So here's inflated 2. So now average. So if you now average, what you'll end up with, so you'll first get rid of all the you get rid of the sulci and get rid of all the crinkles, and then average. And that surface will look like an inflated surface. So this one is, this one is called, smooth white matter. This one is called this surface is called inflated here. So average smooth white matter. What is this one? This one is called inflated average. Well, which makes sense. You just average the inflated. And that's a better one. So that one is not shrunken. And it looks like a normal inflated brain. So this guy is not shrunken. Now, the downside of this is you've got to do everything on the surface in order to use this brain, because if you've done all your stats in 3D, then you're going to have to use this shrunken brain to sample it onto. But another useful thing for this is you can flatten it. If you want to flatten this guy and completely flatten the brain, so you'll notice that if you could flatten this inflated one, but if you did that, you're going to get a shrunken flattening also. So this is a better surface to use for completely flattening the brain, because it won't be shrunken. So that's a small point. So almost nobody uses this surface. I use this surface, but almost nobody uses this surface. But this is the right surface to use for displaying the data, either in inflated view or in flattened view. The problem is you can't easily display the data on this surface in folded view, because then you'd have to go back to the shrunken brain. So that's sort of surface-based statistics. And the main advantage of this is that if you compare, say if you take an area that you can map with other means, like say an area like MT, because you can do visual mapping and find out where area MT is and then outline it. And then take the data, or area V1. Area V1 is very easy to map, and so you map area V1, and so you have an independent measure of where V1 is, and then take the data, average it in 3D, calculate statistics, take the data, do a inflation and sphering, and then registering sphering, and average the data that way. You can see that you have a lot less variance in the borders of something like V1, area V1, if you've done everything on the surface instead of doing it in 3D. And so generally it gives you a big step up in better alignment between different brains, especially in cases where we have some other alternate measure of being able to say where the area is without actually just relying on the fact that our alignment picked up the same vertices. And so that's the main impetus for doing something on the sphere. Obviously, you've got to deal with other parts of the brain that aren't spheres or that aren't surfaces, like say parts of the thalamus or the striatum or things like that. And so that this whole approach is going to have a different approach for the cerebellum or the cortex versus something like some area in the thalamus that doesn't have a well-defined surface. There's maps in parts of the striatum and the thalamus as well, and it's not out of the question that eventually we could start to make surface-based atlases of some of these areas that have these more 3D-like areas that have maps in them. But in general, it's going to be a little more complicated because you've got some areas that are sort of 3D and some areas that are surfaces like the cerebellum and the cerebral cortex. But there's other surfaces down in the brainstem, like the superior colliculus is a surface and it has a map on it. And there's auditory maps down there that are shaped like surfaces. So that's how to align and register surfaces in order to get better cross-subject alignment of data, so that we can do sort of better averaging of data. Okay, so any questions in the last negative 10 minutes about surface-based alignment? Seem okay? So you don't have to do any of this. You can just type in recon all, and all this will happen, and then you'll end up with your surface that's aligned to the sphere, and so that you can then do statistics, sample data onto the FS average surface and calculate statistics on these lists. So, et cetera, down to 160K. Okay, any general questions, specific questions? Go back to the beginning questions. Okay, I think Stan will end there.